Alright, welcome back everybody. In this video we're going to look at the ratio test. And you see the ratio test outlined right here. If we have a series with positive terms and we find the limit as n approaches infinity of the a sub n plus first term divided by the a sub nth term, that's going to give us some limit value L. And really we have one of three possibilities. If L is less than 1, the series converges. If L is greater than 1, the series diverges. And if L equals 1, the test is inconclusive. We can't tell whether it converges or diverges, and we're going to need to use another test to determine if the series converges or diverges. Ratio test is really one of my favorite tests that we'll see in infinite series, and it's one that you'll use probably more than any other test. One thing I will say about this, a lot of times we'll use the ratio test on a series where the argument of the series is a rational function. When we have that, I typically, instead of writing as a fraction like you see there, a lot of times I'll do the limit as n goes to infinity of a sub n plus 1 times the reciprocal of a sub n, because that just generally seems to make it easier for simplification purposes. A simple algebraic step that we can kind of cut out a little bit of our work. Alright, example number 1. Determine if the following series is convergent or divergent. We're going to use the ratio test to do this, and so we're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1. So we're just going to put n plus 1 in here everywhere where there's an n. And the quantity 2n plus 1, when I put n plus 1 in there, becomes 2n plus 3. And this becomes n plus 2. And then I'm going to multiply by the reciprocal of a sub n. So that's 4 to the 2n plus 1 times n plus 1 all over negative 10 to the n. And now I can simplify this a little bit. This turns into the limit as n goes to infinity of negative 10 over 4 squared times n plus 1 over n plus 2. Alright, see, I just took the negative 10 to the n plus 1 and the negative 10 to the n and simplified those to get the negative 10, and I took the 4 to the 2n plus 1 and the 4 to the 2n plus 3, and that gives me a 4 squared in the denominator. And then my n's just stick around in the simplification process because there's no way for me to simplify that. Now, if I take the limit of this as n goes to infinity, the n plus 1 over n plus 2, the limit of that as n goes to infinity is just 1. And so the limit value here is 10 over 16. 10 over 16 is less than 1. Therefore, this series converges. Alright, example 2, determine if this series is convergent or divergent. We'll have the limit as n goes to infinity of the n plus first term, which is going to be n plus 1 factorial over 5 to the n plus 1 times the reciprocal 5 to the n over n factorial. And we're going to simplify this. We end up with a 5 in the denominator. And it's not as obvious to some, I guess, but realize that n plus 1 factorial is equal to n factorial, it's all the numbers up to n multiplied together, times n plus 1. And so when we simplify this, we end up with just an n plus 1 in the numerator, and all the other factors from the factorials cancel each other out. If I take the limit of this as n goes to infinity, that ends up being infinite. Infinity is bigger than 1. Understatement of the day. Infinity is bigger than 1. Therefore, this series diverges. All right, let's go on to example 3. We'll take the limit as n goes to infinity of the absolute value of a sub n plus 1, so 9 to the n plus 1, over negative 2 to the n plus 2 times n plus 1 times the reciprocal of the nth term. It's negative 2 to the n plus 1 times n, all over 9 to the n plus 1. No, 9 to the n, pardon me. Got a little bit ahead of myself there. Alright, and now we'll simplify this. And we end up with a 9 in the numerator and a negative 2 in the denominator, and n over n plus 1. And if we take this limit as n goes to infinity, we end up with 9 halves. 9 halves is greater than 1. Therefore, this series diverges. So that's a quick, neat test we can use to determine if a series is convergent or divergent. Really showing off its impressive range here. Let's determine if this series is convergent or divergent. This turns into the limit as n goes to infinity of negative 1 times n squared plus 1 over n squared plus 2n plus 2, doesn't really matter. The limit of this as n goes to infinity is just going to be 1, which is equal to 1. Therefore, in this case, the ratio test is inconclusive. Whenever we get 1 as the value of the limit, we can't tell from this test whether this series converges or diverges. We're going to need to use another test to determine whether it's convergent or divergent. All right, example 5. A little bit different from all the other examples we've looked at so far. Find the radius of convergence of the power series. We're going to use the ratio test to do this. Setting up the ratio test, the limit as n goes to infinity of the n plus first term times the reciprocal and simplifying this, we get that the limit as n approaches infinity of, let's see, negative 1 times the quantity x plus 1 times n over n plus 1. And if we take this limit as n goes to infinity, this is negative 1 times the quantity x plus 1. Now, in order for this series to converge, we need this output that we got from the ratio test. We need that to be less than 1. Or really, we need the absolute value of this to be less than 1. And so, that means that what's inside that absolute value has to be between negative 1 and 1. And we can find the interval of convergence by solving this inequality. We multiply all three parts by -1. We subtract 1 from all three parts. And so the interval of convergence is from -2 to 0. And the radius of convergence is half the length of this interval. So the radius of convergence here is just going to be 1. All right, so that's a couple of the ways that we can use the ratio test. We can either use it to show that a series converges or diverges, or when we have these series that have a variable x inside of them, we can use them to determine the radius of convergence and interval of convergence by knowing that the absolute value of the ratio test's result right here, that has to be less than 1 in order for it to converge. All right, that's the end of this video on the ratio test. Hope you enjoyed it. See you guys next time. Have a great rest of your day.